Countdown to lecture. Welcome to Friday. Yay. So, no star problem today. Mostly because I looked at the problems at the end of the section and it just, I say that there's always something to talk about, and there is always something to talk about, but the ones at the end of this section are pretty computational. So I just decided to let it go for now. But the others, everything due Monday. Monday we will do section 13.4. You'll get a few exercises to do then. Chances are and then the exam here is on chapters 12 and 13, including sections 13.4, or section 13.4. You're going to have to sort of jump on that homework and do it. I'm not going to collect it. You just have to make sure you ask questions and so forth during the week so that you understand the 13.4 stuff before the exam. All right? It's one section. Here on Wednesday we will review mostly chapter 13, but I might sprinkle a couple of chapter 12 questions in there. And I just want to talk a little bit about your preparation for the exam. Maybe a lot of bit about the preparation, but you can expect problems that are very similar to the homework problems. What you're going to get are on the order of 10 or so problems like homework problems. You'll get a test sheet with, say, 10 questions on it. You'll get some blank paper. You'll write your answers on the blank paper and hand it to me. I'll read through it, give it partial credit, get it back to you probably by Monday. You won't need a calculator. You won't need notes or a book or whatever. If there's some sort of peculiar formula that is, I don't feel like you would necessarily have memorized, then you can ask me and I'll either have it already written on the exam or if you want to ask me, I'll make a snap judgment on Friday whether you actually should know something like that. So for example, scalar projection is something that you should know. The dot product cosine identity is something that you should know. The cross product sine identity is something that you should know. Nick?
What about something like the conversion equations between all the different coordinate systems?
Right, so you should know the formulas for x, y, and z in both of those. But the other direction you don't need to know. Okay, so you don't need to know how to get r, theta, and z from x, y, and z, and you don't need, I take it back, you don't need to know formulas for that. You should be able to do that using just straight up trigonometry. Okay. Forgot my train of thought here, but, those formulas in, what was that theorem where, the derivative of the dot product is, r prime dot s plus r dot s prime. Again, that's something that you should know. All right. How do you prepare for this? You review all of these homework problems. You look at problem, like for example, here I skipped problem 4. I have no idea why I skipped problem 4. But you might look at problems 3 and 5, and if 4 is somewhat similar and you're looking for another problem to do it. But if 4 is somehow weird or different, and I'm going to leave that to you to judge, then I probably left it out for a reason. So there's 2 reasons that I would leave a problem out. One is it's an oddball, it's testing, it's exploring something that I'm not really interested in exploring. Or 2, there are 4 problems to find curvature, and I gave you 2 of them. If you want to do the other 2, great. Okay, it's not that there was anything that was particularly different or that I didn't like about them. I just didn't want to dump a whole bunch of problems on you. All right, so when you're reviewing and practicing your exercises, you're going to be making those kinds of judgments. The other thing is, it's not enough to go and sort of do problem 5, and you may not even realize that you're doing it, but you're working on problem 5, and there's just one little thing that you kind of forgot, so you just flip in the book and you're like that, and oh, okay. You're not ready, okay? You've got to do and get up to test conditions, which means your roommate should be able to pluck problem 3 out of here and give it to you, and you can go off in the corner without a book or a calculator, just a pencil and a piece of paper, and do the problem. Then you're ready. Okay. People that get nervous during exams, I have advice for you too. I've got advice for everybody. If you get nervous during exams, there's this word in pedagogy that people talk about called overlearning, and it's related to the notion, or it's related to what sort of people in the armed forces do, or people in firefighters do, or police officers, even emergency room technicians. Right? They drill and they drill and they drill, because when they have to do what they have to do, it's usually quite a stressful situation. And the last thing you want your firefighter to do when he pulls up to the house is, how do I turn the hose on again? You know, they drill, they drill, they drill. When they get out of the truck, they jam that hose into the side of the thing, they pull this lever, they turn this knob, and they're putting your fire out, right? That's what you want to do. So if you do a problem and you struggle through problem 5 and you look at the book a couple of times while you do it, as soon as you're done, do it again. As soon as you're done, do it again. And I'm not saying everybody has to do that. I'm saying if there are people in here, and you know who you are, who get into a test situation and you start locking up, overlearn it. And it doesn't hurt to do the same problem several times till you can literally by rote write it down. Because you'd be surprised to know that even if you're doing a problem by rote, when you get to step C and you want to get on to step D, you're still making that linkage. Even though it's by rote, you're still triggering a logical flow or a logical conclusion. And what you might find if you overlearn this stuff is, if you get into a problem that's not like the one that you did, and you get to a certain point, your brain's going to say, oh, I'm here, I need to go here. And lo and behold, your brain is actually right, and it didn't even have to think about it. It just went there because it had done that so many times before. So overlearning, I'm a big fan of overlearning if you're having trouble with in-class exams. It takes time, unfortunately. But I am a personal practitioner of this. In fact, in this class, when I took this class at Penn State, I was having a hell of a time with the multiple integrals, visualizing like double and triple integrals. And I knew going into the exam that if I didn't do something, I was going to be hosed. And the instructor gave us this sheet of like 200 multiple integrals, and I did like every other one of them one night, like so 100 of these multiple integrals. And then I walked away, and then the next night I went through them, and there's only so many of them, only so much variety before your brain just figures it out. And did fine on the exam. I was worried, overlearned it, did fine. Okay. Any other questions about the test? Not that there were any questions to start that, but any questions? How about on the current homework? Wow. Suppose that the magnitude of r is equal to a constant. This means that r describes some path on the sphere of radius k with center at the origin. Is that really what that means? Do you understand why that means that? Let's pretend that I'm on the Earth, right? In fact, my trajectory on the Earth as I walk around or as I fly to a conference in California or whatever, my trajectory is precisely one of these trajectories. Why is it? Because my distance from me to the center of the Earth is a constant. And that's true for everybody that roams around on the globe. So this mathematical statement actually has quite a lot of relevance to what we do on the Earth. So my path restricted to the Earth is the same as this path restricted to the sphere of radius k. Show that r is perpendicular to r prime at every point. Okay. My hint, Lila, and anyone else who might be interested, is that the length of r squared is equal to r dot r. And r dot r is equal to k squared. Is that enough of a hint? Good. Okay, and just to finish off that bit of geometric discussion, show that r is perpendicular to r prime. Remember what r prime is. It points tangent to the curve, or tangent to my trajectory, right? So if I'm walking around on the Earth, if I'm restricted to the surface of a sphere, my tangent vector, the tangent vector to my motion, is also tangent to the sphere, right? And this other guy, r, if you think of it as a displacement vector from the center of the Earth to where I currently am, and then I look at my tangent vector, r prime, it's pretty clear that they're perpendicular. No matter where I roam on the surface of the Earth, my tangent vector, no matter how squirrely it is, that tangent vector is always going to be perpendicular to the position vector from the center of the Earth to where I currently am. Make sense?
So for that, you don't want us to use like the fact that any point on or tangent to a circle is perpendicular to the radius, because that's something that is.
I think the intent, I mean, there are different ways of doing this, but I think the intent was to leverage that dot product identity that's in the derivative of a dot product, right? R prime dot r plus r dot r prime. Okay. Okay? Other questions? Yes?
Number 3 of the workbook.
Okay. Good. That one? All right. Find the parametric equations for the tangent line at the point. So going back to chapter 12 to come up with the equation of a line, you need a point and a direction. We have a point. That's this guy. We need a direction. Remember that the derivative of a trajectory, the derivative of a curve points tangent to the curve, or it points in the direction of the curve. So the key here, I think, is probably just trying to figure out which t you want. All right, so which t do we need to plug into r prime to get this direction vector? Is that possibly the question?
Yeah.
Okay.
I think about it.
Okay. And a strong hint is the fact that you have a pi over 6 here and a t here. Okay. Other questions? Lila?
Will you go over the derivative of t on 4 on the web work? Because I tried it with the hint you suggested.
Yeah.
And I still.
I just got an email from a student saying she did this, she struggled with it for a while, thought she got it right, plugged in 1, got the wrong answer, and then just on a whim, and I really like this because this is a true mathematician, decided to plug 1 into t and stuck that answer in there, and that was right. So that's a typo. Sorry about that. I just literally got the email from the student between classes. I can't confirm that that's true. I will confirm. I will check that after class. But
Yeah, because no, because since it's t derivative, it looks like t derivative of 1. It's just really, really ugly. Like, really awful.
so is it 0? I don't know. I can't tell which one it is, but. Wow, that's just a lot of stuff there, isn't it? Anyway, so possibly there's a typo there. Other questions? All right. Today we talk about, let me pull that back up. We're going to talk about arc length and curvature. Arc length is a really nice application of integration that we'll explore, and then we'll finish with a discussion of curvature. Curvature measures how much a curve wants to bend. So you take a point on the curve, and if it's really bending sharply at that point, then it's going to have a high curvature. And contrast that with, say, contrast that with, say, a straight line, which is not bending at all. Straight lines have zero curvature all along them. And so we want to develop this quantity and use it to describe the geometry of curves. It's a way of saying, a really high curvature at a particular point means that that particle is really making a hard turn at that particular location. So those two things are what we have in mind. There's a lot of stuff between here and the end of class. Bear with me. You are going to have to read the section here to really drive this stuff home. And let's get going here. Okay, what I want to start with is arc length. And it makes perfect sense for a curve R of t to ask the question, how far is it from here to here? How do you spell stretch anyway? TCH? Yeah, there we go. Okay. How long is this stretch of curve? And we can provide a fairly nice answer using calculus, using integration. So I'm going to draw in an origin, and I'm going to fan out a few radii. So let me just sort of carefully put these in here. And along each of these guys, I'm going to put in, so these are all just vectors. Along each of these guys, I'm going to put in little displacement vectors. Now, it may not be clear from the drawing, but the displacement vectors are straight, and the curve is curvy. So what we want to do is use the length of one of these straight displacement vectors to approximate the length of the curve in that little chunk. And then, similar to what we did with Riemann sums back in Calc 2, what we'd like to do is take that fan of vectors and just multiply it, chop it up even finer and finer, use those displacement vectors, add them all up, and get a good rock-solid arc length by integrating. That's the goal. Okay, what I want to do is focus on just one of these guys. If we focus on just that one guy, ooh, terrible drawing today. Let's put that there, that there. Let's do the curve in through here. Let me get my hands on a different color. And I'm going to sort of shorthand some of this stuff just for the sake of time. Right, and I'm going to say that this is the position at RT sub I, and this is the position at RT sub I plus 1. Okay, so what am I doing? What are these TIs and TI plus 1s? I've taken the interval from A to B and I've chopped it up into lots of pieces. This is in T, and the consecutive points TI, TI plus 1 are what I'm interested in, right? These are these two locations corresponding to TI, TI plus 1. Okay, and I'm going to let delta T equal TI plus 1 minus TI. Another way to write it is just B minus A over some N, where N is the number of subintervals that I'm chopping up into. Okay, now, back to the basics. What I want to do is approximate this little chunk of curve by that red arrow. Nick?
So can you repeat, what's the G there for the TI plus 1 minus TI?
Delta T, capital delta T. Yeah, it does look like a G, doesn't it? Okay. There. The vector, the red vector, is given by RTI plus 1 minus RTI. Right? It's just the displacement from one point to the other. So I subtract the two vectors. The magnitude of this thing, well, just put vertical bars around it. Yay, math. Okay, so I don't have to work too hard to compute the magnitude. I just put vertical bars around it. Okay, I'd like to sum up all these little distances. Yeah? So we're going to approximate L by adding up all these guys. So far, so good. I'm not going to put my index of summation in there. Just we're adding them all up. Okay, and now I'm going to do a little bit of an algebraic trick. So L is well approximated by the sum of these guys, so long as there's enough, as long as I've chopped up the curve into enough tiny little pieces. We'll say that the arc length is well approximated by this sum. And then before I do something, I'm going to do a little algebraic trick. In fact, let me, yeah, I'll just call it delta T. I'm going to divide by delta T and multiply by delta T. And now this looks like a Riemann sum. And what do we like to do to Riemann sums? We like to let capital N go to infinity. And if we let capital N go to infinity, this turns into the integral a to b. What happens to the delta t at the end? Do you remember? It doesn't go to 0 in this context, right? It turns into a dt. And what I'm really interested in is this thing here. As n goes to infinity, what's happening to delta t, or in other words, what's happening to the lengths of the little subintervals? Right? They're getting smaller. Okay? So what's happening to this thing? What does this thing look like?
the slope, getting closer to the slope.
It's the thing inside the vertical bars is starting to look like r prime of t. That's the definition of r prime of t in a sense. It's the limit of the difference quotient as delta t goes to 0. You may be a little bit worried about this. Ti plus 1 is secretly ti plus delta t. Right? To get from one ti to the next ti, you just add delta t. Okay? So now it looks a whole lot like the difference quotient. And what we get is the arc length. In other words, the length of the piece of curve between t equals a and t equals b is just the integral of the magnitude, or the speed, the magnitude of r prime between a and b. Let's apply this to a curve where we already know the answer, just to convince ourselves that this works. So let's apply this to so what's a parameterization of a circle of radius 2? Centered at the origin. 2 cosine t, 2 sine t. Okay. What's the answer? Right. Oh, and I guess I should be a little bit more careful. For t between 0 and 2 pi. So for t on the interval 0 to 2 pi, how long is this curve? 4 pi, right? So we can use the circumference formula. Which you'll recall is 2 pi r, right? In this case, r is 2. We get the circumference is 4 pi. Now, if this is a useful formula, when we compute this using the arc length formula, we should get 4 pi. Let's confirm that. You need to fill in all the pieces. So to start with, we need r prime of t, which is simply minus 2 sine t, 2 cosine t. And now we need the magnitude of r prime of t, which is 4 sine squared t plus 4 cosine squared t, square root. That's simply the square root of 4. Oops. 2. Everybody follow that calculation? Now, what do I do with that 2? I drop it into the formula for L. What are the limits of integration, a and b, in this problem? 0 to 2 pi. Good. And now it's just a Calc 2 problem. Reassuring, not earth-shattering, but reassuring. All right, let's do this to a somewhat more interesting example. So I want to take my circle and turn it into a helix. What do I do? So we'll put a t in there. Lots of things we could have put in there. We'll put a t in there. So by putting a t in there, the circle is now no longer restricted to the xy plane, but as t increases, the z coordinate increases, and it rises up out of the plane in a helix. Okay. Let's stay on the same interval, and let's think about this qualitatively. L, longer, the same, shorter than the previous example? Longer, right? Because not only does it trace out a circle when I look down above, but in fact it has to rise up. How many units from beginning to end?
2 pi.
It has to go up 2 pi. So it necessarily has to be longer. There's just no way around it. Let's see how much longer. So it must be longer than the previous example. The calculation is very similar. So we'll grab r prime. And we'll grab the magnitude of r prime. And this is where you begin to see the difference. That's really 4 plus 1 square root, aka root 5. So at this point in the calculation earlier, we had a 2, right? And now we've got a root 5. And which one's bigger? Root 5, right? Because root 4 is 2, root 5 has to be bigger. But let's finish the calculation. So the arc length here is 2 pi root 5. And we've observed already that this is longer. So that's reassuring. I mentioned when I dropped this t in here that there were a lot of choices here. What if I had put 1/2 t in there? How long would that result have been? Yeah. It would have been somewhere between this 2 root 5 pi and 4 pi. 1/3, 1/4, 1/10, 1/100th t. All of those values are going to be less than this result and still bigger than the other result, right? Because if I put anything at all out here in this coordinate, it's got to get longer. How do I make, what would I have to do out there in the third coordinate to get bigger than this length? 2t, 5t, 100t, right? So any coefficient bigger than 1 will make a result longer than this. Any coefficient between 0 and 1 will make a result smaller than this. But no matter what coefficient I put on there, it's going to be bigger than the circle. Longer than the circle. Yeah? Okay. So that's a good qualitative understanding of the arc length calculation. So this result, arc length, it gives us the length between two fixed points. And mathematicians, never being satisfied with what they have, always want to sort of move forward. And what we want to do next is we want to build something called the arc length function. And here, what you do is you have your generic curve, you have your starting point, t equals a, and we have some intermediate point, t. And we want to know the length of this as t varies. So maybe I want to wiggle this t back and forth a little bit, right? If I move this t backwards this way, it's going to get smaller. The arc length is going to get smaller. And if I move it down that way, it's going to get longer. And what I want to understand is how does L depend on t? t. So I have a fixed starting point and a variable endpoint. Does everybody understand that? Easy enough to build. You just take the old arc length formula and you replace B with T. Right? So instead of having this fixed end at B, we now allow the end to vary a little bit. And what we want to see is how does this thing behave as a function of T. You'll also notice, in keeping with calculus etiquette, let's go back to this formula. The original formula was A to B, R prime to T, magnitude dt. What's different down here? I'm using U as my dummy variable. Why?
Because T is...
Because I've got a T in my limit of integration, and that's just good etiquette. Okay. So that U is simply a dummy variable to make this work. Let's make a few observations about S. Oops, not obesations. Observations. S prime. What's the derivative of S with respect to T? We have a theorem for this from Calc 2. Nick?
Is it just R prime of T, or the magnitude of T?
Yes. And what theorem did you apply?
I don't know the name of it, but
Starts with an F. Fundamental theorem of calculus. Okay? That's the fundamental theorem of calculus. And what we notice here is something that should make a little bit of sense if you start parsing the symbols. The rate of change of arc length is equal to the speed. No mystery there, right? That makes sense. The rate of change of arc length is equal to the speed. A couple of other subtler observations. S of t is continuous. S of t, as we just observed, is differentiable. S of t is monotone, increasing. S of t is invertible. There's probably other things that I could say about S, but these are the biggies. For example, how do I know that S of t is increasing?
You can't add negative length. S of T is the length of the...
I agree with you, right? And so as I move out, how about a more mathy Calc 1 way of proving that to me? S prime is the magnitude of R prime, which is positive. Therefore, S prime is positive. Therefore, S is increasing. Yes? Pretty straightforward. S prime is invertible. You may not have thought too much about invertibility in a while anyway. Do you remember how to find the inverse of a function? Lila?
You switch them.
So switch the x and y and then solve for y again, right? Trivial process? Can be extremely hairy, right? Depending on what the function is. Can be a mess. Here we would be switching t and s and solving, right? Okay. So, and it can be messy. I just want to note that however messy it might be, theoretically, it's possible to do because it's monotone increasing. Therefore, it's 1-to-1. Therefore, it's invertible. Just keep that in mind. I'm not saying you can always do it. I'm just saying that it's possible. Okay. Yes, possibly. The only time you're going to be asked to invert S is in very straightforward cases. For example, let's find S of t for R of t equals 2 cosine t to sine t 0. All right. So we need R prime, which we've already done several times now. And we need the magnitude of R prime, which turns out to be 2. Okay, so now we're ready for S of t. This is one of the examples where you can actually do this exercise. 2 du, 2u, 0 to t, 2t. So S of t is 2t. What's the inverse of S of t? T of S. Got to be careful how you say that, right, Nick? Okay, half S. So yeah, 1/2 S, and pretty straightforward. I should tell you that even for the next sort of most simple curve, like change the circle to an ellipse, you can't find T of S. It exists, but you can't calculate it. Okay, so we're going to keep things very straightforward. We're going to, the examples and the exercises, etc., are all going to be exercises that you can actually do these calculations. But you should know that in the real world, you're extremely limited in the class of functions that you can actually do these calculations. Okay, so there's an example of the arc length function, and what this tells you is how far down the curve you've gone after, say, t seconds. And then there's this inverse thing, and you might be wondering why I'm even worrying about the inverse. And let me start talking about that. Yes, I should start talking about that. Okay. So you've seen examples. You've seen examples, for example, R1 of t equals, say, 2 cosine t to sine t 0, and R2 of t 2 cosine 2t to sine 2t 0. Same curve, 2 parameterizations. Okay? Same curve, 2 parameterizations. R prime here, we've done it several times, is going to be different from R prime here, right? Why is the derivative of this going to be different than the derivative of this? The chain rule is going to introduce a factor of 2 everywhere, right? And so there's something fundamentally different about these two guys, even though they trace out the same shape. Sometimes that difference is important, especially in physics applications. Other times in geometry applications, we're not interested in that issue. And so the arc length function gives us a way of removing this dependence on the particular parameterization. So this R2 is a reparameterization of R1. Same curve, just a different formula that you're using to get there. Are all parameterizations created equally? Not really. There's one parameterization that's better than all the rest, and that's what I want to talk about right now. Okay, here's an aside. Let's say you want to give me, you ask me how to get to Portland. So what do I say? I say, go 30 miles west on 12-ish, and then it's going to turn into 7:30, I think, and then keep going maybe another 20, 30 miles west along the river there, and then, you know, you have some options, but basically what's going to happen is you're going to hit the highway, Interstate 82, and then you're going to keep going west another 200 miles or so, and now you're in Portland. Okay, let's talk about those instructions. When I say go 30 miles west on 12, is that as the crow flies? No, it's as I go along Route 12, right? So when I'm driving on Route 12, the odometer is actually measuring arc length. It's measuring my distance along 12, not as the crow flies from one point to the other. So it makes a lot of sense to tell somebody to go 30 miles west on 12, because that is unambiguous. If you go 30 miles west on 12 and Ryan goes 30 miles west on 12, you're going to be in the same place, right? But if I say go an hour west on 12 to both of you guys, then it depends on how fast you guys drive, right? Okay, so there's something unambiguous about that kind of instruction, about that kind of way of locating yourself on a curve. And that's what I want to talk about now. So the arc length parameterization. Now I'm going to start throwing around a lot of symbols, and you just got to sort of strap in and let it go. All right, I'm going to start throwing around lots of ds, dt's, and things like that. Just sort of let it wash over you. This is more of sort of it's a bit of an aside. It has a purpose, but I don't want us to really dwell on this a whole lot. I'm going to do it, and we'll just see where we are at the end. Arc length parameterization. So suppose you have R of t. Then build S of t. Then get t of s. And I'm saying all these things like they're easy, and they're not. Get t of s. Then define beta of s to be r of t of s. Beta is the arc length parameterization of R. Okay, on the side here, just notationally, okay, so when you're reading the book, If you see an S, that usually means that it's an arc length parameterization. It's referring to distance along the curve. And T, usually you can't assume anything. It's just arbitrary parameterization. All right. So you're given some function, or some trajectory R. You build the arc length function, which can be onerous. You find T of S, which could also be pretty onerous. And then you define B of S as the composition of R and T of S. Now you have precisely what I just described on driving to Portland. If I say go along the curve 6 feet, that's unambiguous. I start at this point, I go out 6 feet, I'm here. That's unambiguous. Okay. What's good about this arc length parameterization? Because it surely is difficult to find. Here's a theorem. If beta of S is arc length parameterized, then the magnitude of beta of S is 1. So any curve at all, if you reparameterize it to arc length and you compute its speed, it'll be 1. I'll do a brief proof of this. Again, it's not, you don't have to reproduce this proof. So arc length parameter, let's do, so we know that beta of S is equal to R of T of S. Let's differentiate that. Beta prime of S is R prime of T of S times T prime of S. That's just chain rule, right? Okay. Now we have to start figuring out what these primes mean. This prime here is the derivative with respect to S. This prime here, from the chain rule, is the derivative with respect to what? It's a tough question. It may be one that you haven't ever really thought about before. That's dr dt, evaluated at T of S, times dt ds, the derivative of T with respect to S. That's secretly, that's how the chain rule is actually working. Right? You differentiate this guy with respect to its original variable, and then you plug this in. Okay, that's how the chain rule works. Okay, let me make an observation here. You see mathematicians do this a lot. I'm not going to really justify it here. Suffice to say, it's in your calc book. If you have, if you go read, boy, where is that? I want to say it would be in the Calc 1 section, and it's called, in a lot of books, it's called the inverse function theorem. So if you go searching through the index for something like inverse function theorem, it lets me say that dt ds is really just 1 over ds dt. And it's, I'm not going to dwell on that other than to say that it's in the calc book. Why do I care about ds dt? Go way back. I don't know how far back. Notice here that ds dt is this. Take the magnitude of both sides. I'll just do it right here. And you get unit speed. Okay. Yeah.
What happened to that T of S?
I suppressed it, so it's still hiding in there, and they're both evaluated at the same place, so it's okay. Yep. Yeah. Okay, so if you reparameterize a curve according to arc length, the result will be a unit speed curve. That's what these are called, unit speed curves. Let's do this to our friendly circle example. Let's reparameterize r of t to cosine t to sine t, and we'll leave it at 0. Okay, I think we already did s of t for this, and it was 2t, and stay. And so t of s was just 1/2 s. And so the reparameterization beta of s is r of t of s, which means everywhere I see a t, I want to replace it with an s over 2. And there's a reparameterization, an arc length reparameterization. And you'll see how this beta prime thing works. Beta prime is -2 times 1/2 sine s over 2, 2 times 1/2 cosine s over 2, 0. And notice that this parameterization is perfectly designed to cancel out the 2's. And what's the magnitude of beta prime? It's 1, not surprisingly. So I started out with this somewhat arbitrary parameterization up top in terms of t. I found s of t, I found t of s, I built r of t of s, and that's an arc length parameterization. What does this give me? Well, for example, where am I if I travel pi units along beta of s? Where am I if I travel pi units along beta of s? Well, that's just a matter of plugging pi into beta of s. And what does that give me? Beta of s is right here. Plug pi in for s. You can do it. 0, 2, 0. Is that the right place? Does that make sense? Well, x is 0 and y is 2, so I'm at the top of the circle, right? And I traveled pi units. So after I traveled pi units, I was at the top of the circle. Is that right? Well, what's the circumference of this circle? Remember way back when we first started this whole ordeal? Do you remember what the circumference of this circle was? 4 pi. If I travel pi units along, I've gone how far around the circle? 1/4 of the way. That's 0, 2, right? That's the top. 0x, 2y. So this guy tells me, it answers the question, where am I if I go x units along the path? And this is frankly the more natural way. If you think about how we talk about moving around, we usually use the arc length parameterization. Go a mile down this path, go 30 miles down this road. And that's unambiguous. So this is a mathematical way of encapsulating that idea. And it's a really good idea. Let me finish with a discussion of curvature. Okay, we're going to assume beta is unit speed. And that's the same as saying arc length parameterization. What's T? If I have beta and I want to find T, how do I find it? Yep, it's in here somewhere. There it is. Except I'm doing it on beta, right? So it's what? Beta prime over the magnitude of beta prime? I know, I'm getting there, Lila. So in this case, the unit tangent vector for a unit speed curve, the unit tangent vector is easy to compute. It's just beta prime. Okay? As opposed to, in general, it's r prime over the magnitude of r prime. And so there's this extra step that you would have to do. Okay. Curvature is kappa of s is the magnitude of t prime. That's its definition. Why is this the definition? I mean, we'll explore that a little bit if we have time. T is the unit tangent vector. T prime, qualitatively speaking, tells me how t changes, right? That's what derivatives do. They describe change. So t prime tells me how t changes. The magnitude of t prime, kind of still tells me how t changes. And we're going to call that kappa. Why? This kind of tells me how the curve wants to bend. Right? Here's the curve. Here's the tangent to the curve. T prime tells me how this guy is about to change, or how it is changing at that moment. And the magnitude of T prime is telling me how quickly it's changing. If this guy is going to change really quickly, I want that to be a big curvature. Whereas if it's a straight line, what's the tangent? The tangent is just the direction. What's the derivative of the tangent? 0. What's the magnitude of the tangent? 0. What's the curvature? 0. So this quantity we're going to call curvature. And the bigger it is, the more the thing wants to bend at that moment. This is a really pleasant quantity to compute if you have a unit speed curve. It's really just the magnitude of beta double prime. Problem is, most of the time, you're not given a unit speed curve. So I guess what I'll finish with, and I think in exchange for another derivation, I'm going to do an example. I'm going to finish with how you find curvature if you don't have a unit speed curve. So what if you're stuck with R, non-unit speed, annoying thing that it is? Here's a nice formula. Oops, not alpha, R. So lovely unit speed curves, you want curvature, take the derivative twice and take the magnitude. If it's not unit speed, a little bit more work. Got to find r prime, got to find r double prime, find the cross product, find the magnitude, divide by the magnitude of r prime cubed. I will say that this is better than, usually, it's better than reparameterizing. In fact, sometimes, for example, if you have an ellipse, you can't reparameterize it because you can't find the inverse of s of t. And so in that situation, this is literally all you have. Let's do an example. And I'll just pull one from the back of the book here. If you look at the back of the book, 1 through 3, I think you guys are at least okay with. Is everybody comfortable with this notation? I've been using it a little bit. That's the same as just saying 0 less than t less than 2 pi. It's just interval notation. And that funny looking e there is a mathematical symbol that means is an element of. T is an element of the interval 0 to 2 pi. And you'll see me use it. You'll see lots of people use it. This guy, these 3 guys, right? Just a fairly straightforward application of the arc length formula. So take the derivative, find the magnitude, integrate, and you're done. Some of these integrals can be a little dicey, but 6 through 8, find the curvature of, say, t squared, and t. Well, that's presumably not a unit speed curve, right? Because they didn't tell you it was unit speed, and it doesn't really look like it's unit speed. How could you figure out whether it was unit speed or not? Take the magnitude of the derivative, and if you plug in a t and you get anything other than 1, then it's not unit speed. Which means what in terms of finding curvature? You got to use the other formula. You got to use the cross product formula. So I'm just going to assume that t squared t is not unit speed. I'm pretty sure that's the case. In fact, we could probably verify that along the way. So this is 13.3, number 6. Not unit speed. Just start collecting all the things that you need. You need r prime. You need r double prime. Lots of zeros, I like that. I often write it like this because now it's all nice and ready for a cross product. Let's do the cross product. So it's 0 minus 2, 0, 2. Not so bad. Magnitude of the cross product. 4 plus 4, 8, root 8, 2 root 2. Got the numerator. Denominator, magnitude of r prime. A little dicier. 1 plus 4t squared plus 1 root 2 plus 2t squared, not 2, 4t squared. Don't forget to cube that thing. Kappa of t is 2 root 2 over 2 plus 4t squared to the 3 halves. You can understand a little bit about the geometry of this curve. Where is this curve bending most rapidly? T equals 0? At t equals 0, it's 2 root 2 over 2 to the 3 halves, whatever that is. It probably simplifies to something lovely. anytime you move away from t, this number's getting smaller, right? And in fact, if you went way out towards the end of this curve, it would start looking like a line, right? It looks like it has very tiny curvature, right? So it has a big bend right near t equals 0, and then away from t equals 0, it starts to flatten out like a line. That's how you use curvature qualitatively. Any questions? Have an excellent weekend. See you Monday.
What?